standard error of the mean. Here the standard error of the mean means it's a standard deviation of mean, sample mean. So this is the sampling error of sample mean is described by it's a standard deviation, right? And then that is what we call the standard error of the mean. So standard error of mean is a standard deviation of x bar. So what is the standard deviation of x bar? So this will be different than standard deviation of x, right? So original population has a standard deviation, but we are not talking about that. But if you collect the sample and then if you calculated the mean, sample mean, what will be the standard deviation of the sample mean? Okay, that is this number, and that is what we call the standard error of the mean. So standard error of the mean, which is the standard deviation of x bar, will be calculated by this one. So this is the standard deviation of the population. So individual x standard deviation, but x bar will be different because we are adding up. So as a result, this standard error of the mean will be smaller than usually the population standard deviation. Why this thing's happening? Because when you add up some number, the bigger number and smaller number add up and then cancel out each other. So whenever you add up, actually the result will have a smaller variance. That's why usually standard error of mean is smaller than the population standard deviation. But how much it will be smaller will be defined, affected by the sample size. If the sample size is more and more, so if you add more and more, actually plus minus cancel out happen more, so it will be way smaller than the population standard deviation. So for example, if the mean is the $80, so this is a customer's spending, facial treatment, spending is $80, mean $80, the standard deviation is $10. But if you collected a random sample of 20, and then if you calculate the mean of that 20 sample, mean for 20 sample, that mean of the 20 sample will have a 2.236 standard deviation. So that will be the way smaller than the 10. So as I told you, the normal distribution, this is the original population distribution, but when you calculate the x bar, which means you add up, that's why the bigger number, smaller number cancel out, the smaller standard deviation. So population may not have a normal distribution. So as I told you, by central limit theorem, if you have enough number of sample, doesn't matter what was the population standard deviation, population distribution, the x bar can be assumed to be a normal distribution. However, now how big n we need, right? So we said enough number of sample, then we can say the x bar, the sample mean, will follow the normal distribution. By central limit theorem, it doesn't matter what was the original one. Uniform, if you calculate x bar, it will be normal. Triangle population, x bar will be normal. Skewed population, x bar will be the normal and normal. But if the original population was a normal distribution, any n will be fine. Any n. X bar will be normal distribution. However, if we have like a skewed, some weird distribution, maybe you can have some weird distribution. X bar will be the normal, but it need a more sample. So rule of thumb will be the n is greater than equal to 30. So we will see this, but so if your population is normal, then any n will be fine. But if it's not, you need more n. But rule of thumb is that if n is sample size is greater than 30, then we can assume whatever the original population was, your x bar will be the normal distribution. So this shows you, so if often use the rule of thumb is n is greater than 30, as you can see, if you add up to the normal uniform population, I think we saw this similar graph in the dice, right? Multiple dice. If you add up to the number of the from the multiple die, the summation will follow the normal distribution. Even this is like a skewed population. If you just keep adding, it will form similar to the normal distribution. Of course, when this is a skewed population, it requires more sample size to become a normal distribution. So range of the sample mean. So we can talk about it. If original distribution looks like this, right? And then center is mu. And then you can say my x bar will be somewhere here, but x bar, mean of x bar will be mu. That's why, so this graph is a x bars graph, x bars distribution. So center will be the mu because the mean of x bar is mu, and standard deviation of the x bar will be the sigma over square root of n, right? So if you want to give us some range here, then you can use the same way, which is the mean plus minus z sigma, right? But here sigma is, this is the standard deviation of x bar. So if you just replace it, this will be the mu plus minus z and sigma over square root of n, right? So this is the one. So we will talk about the z here a little bit more. If we know the mean, the population mean and population standard deviation, then we can predict the sample mean will be within this range with 90%, within this range with 95%, within this range 90%. But if you look up to this 1.645, actually this number will be different. So z value is 1.6, and 4 and 5. So in between these two numbers. So which means it's a z value which is 1.645. It's related to the probability of 0.95. Okay, but why it was a 90% range? So it's a 90%. Why we are looking for the 95% probability here? The reason is that this table is always show the left hand side here, right? And this area. This table show us this probability. However, if we want to have a 90% range, which means if you want to have a range here, and then I want to have a 90% of this is a fall in this center portion, which means this is 5% and this is 5%, right? So if you want to find out the exact this point, x or z of this point, what should I look for? This is 5%, then this will be the 95%, right? So even though our confidence level is the 90%, That's why when we try to find out this point as a z-value, you have to look for the 95 because this table shows all the way left hand side. That's why it's including this 5 and 90, so we have to look for the 90.95. That's why even though this is 90% range, but we have to look for the probability 0.95, and then we can get a z-value is 1.645. So that's why it's a 90%, but this z-value is actually the 0.95 z-value. Similarly, this z-value is the z-value that is related to probability is 975. Similarly, right? If you want to have this is 95, this should be the 2.5%, right? 2.5%. If you want to find out the z-value here, actually you are looking for the 0.975. Similarly, this z-value is related to the 0.995. Okay, but usually we use a 90, 95, and 99, so you can use this value for the z-value. So let's take an example. So amount of the liquid in a half liter bottle of the Diet Coke is normally distributed with mu is 505 and standard deviation is 1.2 milliliters. So this is population is normal. So when the population is normal, any sample size will be fine. Any sample size. You don't need a big, large sample size to be a sample mean will be the normal. So any sample size, sample mean will be a normal. And then if you want to find out the sample size and it's 4 bottles, so if you sample 4 bottles, and then what we can expect the sample mean lie between the narrow range. So we can find what is the probability in the range. So here, if we choose a sample number n, actually that is the same as the population distribution, right? So if you want a 95% range, then we can use a z-value, 95% range z-value. Which means it's the 0.975 z-value, and then you can find the z 0.975. Again, this is because our table showed all the way down here, but this 95 is not all the way down. This is 95. So this part will be 2.5, this part will be 2.5. If you want to find the same point here, this will be 97.5%. Okay, so that's why it's a little different. So you have to understand why it's different. You should not make a mistake. It's 95%. You are not looking for the 0.95 in the Z table. So now we can use this fact. Actually, what was that? The X bar is fall in between here, right? Z and sigma of the square root of n. So how can we change it to the mu? How can I tell about the mu? Then you can just subtract this. Then you can find out the mu will be in the X bar plus minus Z sigma over square root of n, right? So why we change this form to here? Because we will measure the X bar, but what we want to know is where is the population mean, which is the unknown. We don't know. So once we got an X bar and then this confidence interval, so we call this is confidence interval. I don't know what is the mu, but our mu will be fall in between this range. So between means is x bar minus z sigma square root of n, and the upper limit will be the plus. So our mu will fall in between this range. That is our what we call the confidence interval. We have to talk about the what is with maybe 90 or 95 or 99% confidence in confidence. So this is confidence interval. Why this is alpha divided by 2? So here alpha is the this is the alpha. So this is the again, I'm just keep explaining here. This is the 1 minus alpha here, confidence interval. Then this part together should be alpha. So this is alpha divided by 2. This is alpha divided by 2. So that if you add up all the three range, it will becomes 1. Alright, that's why we are looking for the different number here. So 90% confidence interval we are looking for here, but this z value, our table shows you the all the way down. So you have to add these two numbers. So this is a 0.95. In this case, this z value is this plus this. So it's a 0.975. Okay, that's how it works. So choosing the confidence interval, so you can just choose confidence interval. 90%, 1 minus alpha is 0.9, alpha is 0.1. So alpha divided by 2 is a 0.5. So that's why you are looking for these numbers. Okay, so a 95% confidence is most openly used, but mostly it's 90, 95, and 99. But you can have a 98%, or you can have a like 85%. If you want, still you can do. Only difference is you can just look for the different z. So what it means is 90%. Or 95% confidence. Here the 95% confidence, some people said this way is the mu is in the range with 95% probability. But this is wrong. Here 95% confidence does not mean this is a probability 95 probability. The reason is technically this is wrong because mu is the deterministic value. This is not the random value. So there's no probability. It's a mu is in the range or not. It's clear. There's no probability, but however, we can predict this statement. So this is technically wrong statement. You cannot say that. However, if we created this confidence interval, find the x bar and calculate the confidence interval, find the x bar, calculate the confidence interval, find the x bar, confidence interval, and so on. If we do this 100 times, 95 of the confidence interval would contain population mean. So this one doesn't contain population mean actually, right? So it's actually, you might think that's the same thing. No, technically that's a different thing. if we do this confidence interval, find the x bar and then calculate the confidence interval, find the x bar confidence interval. So every time you will collect the different sample, then out of 100 confidence interval, 95 of the confidence interval would contain some mean, the population mean. That is the technically different statement. Then mean, population mean will be in the range with the 95% probability. So this is technically wrong, but this is correct. This is the what we means is 95% confidence. Okay, if the sigma is known, the population standard deviation is known, and the population is normal, then we can use the formula and then easily tell the confidence interval. Actually, the z value is for the normal. And if the standard deviation is known, and then we don't know the population is normal or not. If the population is normal, any n will be fine. If the population is not normal, then we want to have a large n, it's a big enough n, so that we can still say that even though our population is not normal, but x bar will be the normal. Larger n may be needed for the assumed normality if your original population distribution is strongly skewed. However, sample size is more than 30, then yeah, still we can assume x bar is the normal distribution, regardless what is the population distribution was.